Okay, so I'd like to welcome everybody to another edition of the Quantum Computation and Isolation Seminar. So I'm very happy to be introducing Professor Daniel Lidar today. So Professor Lidar got his bachelor's degree in 1989 from the Hebrew University of Jerusalem. And he got his master's degree from 1995, also from the Hebrew University of Jerusalem, and his PhD in 1997, also from the same university under Robert Gerber. From 1997 to 2000, he was a postdoc at University of California, Berkeley, under the Rothschild Foundation. From 2000 to 2005, he was an assistant professor and an associate professor of chemistry at the University of Toronto with cross appointments in physics and math. And from 2005 to present, he's currently the professor of electrical engineering, chemistry, and physics at the University of Southern California. Professor Lidar is a recipient of numerous awards, including the 2017 Guggenheim Fellowship, the 2007 Fellow of the American Physical Society, the 2012 Fellow of the American Association for the Advancement of Science. He's a 2015 Fellow of the Institute of Electrical and Electronics Engineers. He's also received the Sloan Foundation Fellowship, the Young Explorer Award given by the Canadian Institute for Advanced Research for top 20 researchers in Canada under age 40, and the John Charles Poliani Prize in Chemistry. And today he'll be talking about classical boundaries of quantum supremacy. So please help me in welcoming either by unmuting yourselves and clapping or by clapping virtually, Professor Daniel Lidar.
Great. Thank you very much, Josh, for that generous introduction. Let me try to optimize my viewing of my own screen here. Okay, great. Well, it's a real pleasure to be here virtually and to tell you about work that was done with Alexander Zlokapa from Caltech and Sergio Boisha from Google that we called Classical Boundaries of Quantum Supremacy, and the preprint archive number is noted below. So what is this talk going to be about? What's this work about? Well, no doubt everyone present has heard about Google's breakthrough result on quantum supremacy from 2019. The work was highly publicized and has garnered a great number of citations. I think roughly on the same scale as LIGO and gravitational waves and so on. So obviously it's generated a tremendous amount of interest. And what I want to talk about is what this experiment actually means in terms of what was accomplished kind of from a computational physics perspective. Not the nothing about the hardware or the physics of superconducting qubits, any of that. This is really more about what is the meaning of the supremacy result and what can we extrapolate from it. So to start at a very high level, what was shown in the experiment was a breaking of sorts of a classical intractability barrier. What they did was they used their so-called Sycamore chip, this 53 qubit chip that they built back then and are still using, in order to perform a calculation that took 200 seconds that no current classical computer can perform faster. And this was done without any assistance from quantum error correction, and despite the fact that decoherence, as we'll see, was a major factor in the experiment. So obviously this raises a lot of questions, and I've noted a few which I'm going to discuss today. So specifically, how does this generalize? Or in other words, what is the map of quantum advantage in the bigger space of circuits? In that space, I want to define in terms of just the number of qubits and the number of gates for a similar type processor. Suppose we could scale it up. And is there an upper or maybe a lower bound where classical computing becomes supreme relative to quantum computing in this type of experiment? And where does that happen in terms of circuit size? How does it depend on error rates? If it does, what's the right error model? Can we simulate these error models and so on? So all of these questions I would like to address today. And just to give you a preview of the result, this is a plot that will appear at the very end of my talk. In a way, it summarizes the answer to most of these questions. We can indeed plot out a map like this in the space of possible circuits parametrized by depth, which is essentially the number of gates, and width, which is the number of qubits. And we can draw boundaries where classical computing is better than quantum computing. Those are the colored regions there. We can compute the quantum runtime to perform a supremacy type of experiment. And without going into details right now, let me just mention that those red dots you're seeing there, those are essentially all the experiments that the Google group performed in their paper. And you see that these experiments indeed protrude into the white zone, which is where there's a quantum advantage. But it's pretty close to the boundaries of where classical computing would win. So I want to discuss how we generated such a plot, what it means, and how it generalizes. That will be the main gist of the talk. And by the way, please feel free to interrupt. I think we have a relatively small group of audience members, so I would welcome questions, comments, discussion. So feel free. Okay, so in more detail, what is it that the Google experiment looked like? Well, they simulated random circuit. They ran random circuits rather, which had a particular structure compatible with the Sycamore chip. So the Sycamore chip is a tiling of the structure shown here, where the crosses are the qubits, and A, B, C, and D are gates between the qubits. And what they did, these random circuits, they had a very particular structure. They consisted of an alternation of single qubit and 2 qubit gates. The single qubit gates are the random thing here. So they picked square root of x. X is the Pauli sigma x, square root of sigma y. W is the Hadamard gate. So they picked those at random for every qubit. And then immediately thereafter, they applied an I-swap gate between pairs of qubits according to a certain pattern. Right? So what is an I-swap gate? It's a 2 qubit gate that is a member of this family where theta is set equal to pi over 2. And the pattern of these I-swap gates is important because it turns out that some patterns are classically intractable, classically hard, and some patterns, like this periodic pattern here, is classically easier to simulate. They generated numerous random circuits of this type where they varied the single qubit gates, the X, Y, and the W, and they alternated the patterns of these I-swap gates. So every circuit is characterized by its width, that's the number of qubits, and its depth, which is 2 times m, where m is just the number of 1 plus 2 qubit gates. So then you can define the task as random circuit sampling. And so what is random circuit sampling? Suppose you picked a random circuit U. Now you need to sample from the distribution of outcomes. So you prepare the input string. The input state is just all the qubits are in the 0 state. You measure in the computational basis. You get an output bit string, which we'll call X. And the probability of getting X is this quantity here, which I'm calling Q sub U of X. And you do that for a random unitary of size n and m. Okay, so in other words, the task is to generate a bit string X with the right probability Q sub U of X. That's the random circuit sampling task. Okay, and then you can ask, is this task hard classically? And it turns out that we know that the answer to that is yes for ideal, noiseless, decoherence-free circuits. It has been proven that even the average case is already Sharpie hard. So in other words, if you pick a random circuit, you will find that computing this probability q sub u of x is classically very hard. And if you're unfamiliar with the complexity classes, Sharpie is about as hard as it gets. It's even harder than NP. But this is not, there are some caveats here. It's not true for shallow depth circuits. And by shallow depth, what is meant here is that the circuit depth scales logarithmically in the number of qubits. In that case, it's actually classically not hard. But if the circuits are deeper than shallow, as defined this way, then that task becomes very hard. However, of course, in reality, we don't have ideal noiseless circuits. Instead, we have noisy circuits. And you can model the noisy circuits in terms of a CP map, which you might guess has this form. F is a fidelity, I is the identity gate. And so basically what this is saying is that instead of applying the ideal circuit U, which would be applied to a density matrix, U from the left, U dagger from the right, instead with probability F, you apply the ideal circuit U, but with probability 1 minus F, you apply just complete noise, the identity gate, properly normalized. So if that's the case, in reality, what's going to happen is we're not going to sample from the ideal Q sub U here, but rather we will sample from this noisy distribution with E sub U as the actual implementation, the noisy version. And of course, in the high noise limit, right, where let's say we have a almost zero fidelity, then the probability is determined by this identity instead of the original circuit that you wanted to run. And then the distribution over bit strings is just going to be uniform. Yeah, so every bit string will have the same probability. So clearly the hardness of random circuit sampling depends very strongly on F, because it's trivial to simulate the uniform distribution, but it's sharply hard to simulate the actual ideal distribution. And it's been conjectured based on some strongly held conjectures, assumptions in computer science, that for any constant F greater than 0, it's already classically hard to do random circuit sampling classically. Okay, so this is the task, and it's a hard task apparently. And now, how does one quantify what's going on? Well, Google chose to quantify the hardness using a type of fidelity measure called the linear cross-entropy benchmark. And let me define what that is. This is straight from their paper. The linear cross-entropy benchmarking, the Xeb, is defined as an overlap between two distributions. The P sub U here is this ideal distribution that I referred to on the previous slide. But here it's because we can't actually expect a real life quantum computer to give us this distribution. Instead, we pre-compute it classically. Classically, we have a specification of the circuit U. So we can, in principle, run that circuit, run a simulation of that circuit on a classical computer, and we can compute the outcome for every bit string X, and do that without any errors. So that is P sub U. Of course, that's very hard to do. That's the whole point. But let's say that we do it. And then Q sub U is the measured probability on our hardware, our quantum hardware. And so we take the overlap of these two, multiply by 2 to the n, subtract 1. That's the Xeb fidelity. And what does it mean? Well, basically, you can interpret it as meaning it measures the probability that no error has occurred. Okay, so in other words, you can show, and this is actually non-trivial to show, that for a perfectly implemented circuit, this quantity is 1. That's one limit. And in a totally noisy implementation, this is very easy to see, if we set the q sub u equal to 1 over 2 to the n, right, that would be the completely noisy case. Then the 1 over 2 to the n cancels with 2 to the n. You have a sum over the whole distribution. So sum over x of p ux is 1. 1 minus 1, 0. So in the totally noisy case, f of u is 0. So that's the meaning of this quantity. It measures the probability that no error has occurred. But in practice, what is done is we have to sample, right? We run the circuit. We don't actually know the distribution q sub u precisely. Instead, what we have is some kind of an empirical estimate of it. And the empirical estimate is obtained by measuring bit strings, which I've now called x sub I. And you have n sub s samples. So n sub s is the number of samples that you get. And you just run the circuit over and over again. And you get, every time you run it, you get a new bit string, x sub I. And you estimate the actual formula here for the XCB in terms of this quantity, where you plug in your bit string into the pre-computed classical probability. So this is the quantity. The one in blue is the quantity that was actually computed in the experiment. And notice that now it's a random variable because, of course, you get a different set of bit strings every time you run a new circuit. Okay, so this is the quantity that was computed in practice. What did they observe? Well, they ran the experiment for various sizes and various numbers of qubits and various depths. And this is the largest case that they considered. And they found that they got a fidelity of, well, this particular number here. And they did that by collecting 1 million bit strings, and that took 200 seconds. Okay. So then they argued that it would take the world's most powerful classical computer, Summit, 10,000 years to generate 1 million bit strings with the same fidelity. And that estimate turned out to have been too pessimistic because several papers appeared shortly after. And they reduced the 10,000 years figure to a matter of a few days. But so far, nobody has been able to demonstrate that you can actually collect 1 million bit strings giving this fidelity in less than 200 seconds. We're sort of stuck at a few days classically. So in essence, this is the supremacy claim that was made by Google. Okay. So now I want you to note, just for future reference, that there's a relation here between the million and the 10 to the minus 3 of the fidelity. And that's not an accident. We'll get back to that. But before I get into it, I want to talk about how things scale here. This is obviously just one data point at a particular size. And that data is available from the Google experiment, and it's very interesting. There's a lot of information here, but I want to highlight the most important fact, which is that the fidelity as a function of the number of qubits, that's on the left, or as a function of the number of cycles, m. And so here they fix the number of cycles at 14, and they vary the number of qubits. And here on the right, they fix the number of qubits at 53, and they vary the number of cycles. And this is a semi-log plot. So the straight line means, the roughly straight line means that the fidelity decays exponentially. It's exponentially small as a function of the number of qubits and as a function of the number of cycles, which is what you'd expect without any kind of quantum error correction or error suppression. So again, there are a lot of details here, different types of circuits, the different patterns, the classically relatively easy pattern, the classically hard pattern, and so on. But the most important thing is that the fidelity decays exponentially. And the one data point that I highlighted on the previous slide is the one over here at size 53 qubits and 20 cycles. Okay, and this is what they estimated would take 10,000 years. In other words, if you wanted classically to sample 1 million bit strings such that the fidelity would be 2 times 10 to the minus 3, that would take, according to the original estimate, 10,000 years to do. Okay, and now we know that it's more like a day to generate 1 million bit strings like that. But still, this doesn't clarify exactly what the computational task is. So let's take it a step further. So here again is the Xeb fidelity. And the actual computational task, if you think about it in terms of not a particular data point, but rather in terms of some kind of a family of computations, depending on the size and the width, is the following. So the Xeb task is to generate a sample of n sub s bit strings such that this random variable, the Xeb fidelity, can be reliably estimated statistically. Okay, and that means that it should be larger than its own standard deviation. All right, I mean, that is an obvious statistical criterion. If the standard deviation is larger than the quantity you're trying to estimate, then it's statistically not meaningful. So we need to generate enough samples so that you get a reliable statistical estimate of the Xeb fidelity. And then you can declare supremacy, quantum supremacy, if you can do this faster on quantum hardware than on the best available classical hardware with the best available classical algorithm. So now that we've defined the task clearly, essentially it's a statement about these error bars. They have to be sufficiently small. Now we can easily figure out how many samples are needed to solve this Xeb task, because by the central limit theorem, the standard deviation scales like 1 over the square root of the number of samples. So if you plug 1 over the square root of the number of samples in here, and you back out the number of samples, you see that the number of samples basically has to scale like 1 over the fidelity squared. But remember that the fidelity scales down exponentially with circuit size, right, with both the width and the depth. Okay, so that tells us that we're going to need an exponential number of samples. To be more precise about it, we need a model, and we can extract an empirical fidelity model from the data that Google provided. So here again is that plot from their paper. And it turns out that you can fit a single function f that empirically describes both of these curves. And I'll explain on the next slide exactly why it has this particular form. But what I would like to stress right now is that if we use this this fitting function with 2 free parameters, lambda and gamma, and we optimize the values of lambda and gamma, we can get these fits, which are the exact same data. The blue points and the red points are just the Google data from over here. And you see that the fit is pretty good. Right, so the red data is the ones where we fix the number of qubits and we vary the number of cycles m, or the depth, and the blue is when we vary the depth and we fix the number of qubits. So we get a very good fit with just these 2 parameters to all the data. So now we know that indeed the fidelity decays exponentially, right, in both m and n, at least according to our empirical fit. So where does this formula come from for the fidelity? Well, it's based on a very simple stochastic Markovian error model. Let's say that we have a gate set G with gate errors E sub G, and a qubit set Q with qubit errors E sub Q. We could just multiply the respective fidelities of the qubits and the gates, and that will give us the overall fidelity. And what are these EG and EQ, if you like? Well, the gate errors, or the cycle errors, it turns out that for each of the m cycles that we're running, well, clearly we need n single qubit gates, right? That's, as I said on the first slide, that's where we get the random single qubit gates, one on each of the n qubits. And if you think about it for a bit, you'll see that because of the planar architecture of the chip, you need n minus root n over 2 2-qubit gates. Okay, so and that you multiply by m cycles. So m cycles times n 1-qubit gates plus n minus root n over 2 2-qubit gates gives you this. And so that takes care of the gate part of the formula. And then the qubit errors, they scale as a function of n, because for every qubit you have errors due to state preparation and readout. So if you put those two together, you have the first term here, which has some unknown parameter lambda, which we can empirically extract. That is the gate errors. And then the minus gamma n is the qubit state preparation and readout errors. Okay, so we get our lambda and our gamma. All right. So with that, and remember that the number of samples goes like 1 over the fidelity squared. What is the total time needed in a quantum computation that solves the Xeb task? Well, it is the number of samples times the number of layers, m. Okay, that is the total quantum runtime. And so by simply plugging in 1 over f squared for the number of samples, we get this. So that's the quantum runtime. And for the particular values of Google's experiment, where n was 53 and m was 20, and with the values lambda and gamma extracted, you would get 200 seconds. So now let's compare this to classical algorithms, because after all, what we're interested in is finding out when the quantum runtime is smaller than the classical runtime. And here, to do this right, we have to consider all possible classical algorithms that one might be able to use to solve the same task. And of course, that's an infinite set. Well, so we can't do that justice, but we can take the best available known classical algorithms. And there are several of them. And so I want to talk about a few that were actually used in the study, and do a proper comparison between the quantum runtime scaling and the classical runtime scaling. So let's start with the most straightforward of them, which is the so-called Schrodinger algorithm, SA. So the Schrodinger algorithm is the most straightforward thing you can do. You basically just take the circuit as described, and you run that circuit on your classical computer. You don't worry about fidelity. You just assume that the circuit is ideal. And it's not hard to convince yourself that the runtime is going to scale exponentially in the number of qubits. It will be proportional to the number of gates, and there's an extra factor of n here, which doesn't really matter. So this is the straightforward Schrodinger algorithm, just directly simulating the circuit. And if we factor out the quantum runtime, according to the formula above, we get this extra factor here. And you could see that there is a way that the Schrodinger algorithm runtime is going to be smaller than the quantum runtime, because the Schrodinger algorithm runtime doesn't depend on m, on the depth in the exponential, right? So all we need to do in order to beat the quantum algorithm is to make the exponent here negative, right? And that's what's going to happen for this particular threshold value of the depth, which depends on the width, n, right? So it's this formula, it's easy to see. And it turns out that for the particular values of Google's experiment with the lambda and gamma values I mentioned before, you find that the Schrodinger algorithm is going to beat the quantum runtime for 53 qubits, the largest circuit that Google simulated, at a depth of 87, or number of cycles rather. So if they had gone to 87 cycles instead of 20, the Schrodinger algorithm would have won. And asymptotically, with these values of the Sycamore circuit, the Sycamore chip, it gets even better for classical computing. Classical computing wins asymptotically at m equals 71. Okay, so that tells us that already the most straightforward classical algorithm, because of the exponential decay of the quantum fidelity, would win for sufficiently deep quantum circuits. Now, there's also a totally different classical algorithm, which operates in the opposite limit. You see, it depends exponentially on depth m, but it depends only linearly on width n. And so I'm not going to get into the details of this algorithm, but you can read about it in this paper by Bravi, Gossett, and Movosag. And the point is that it can beat the quantum runtime with an exponential advantage in n for any fixed m. Okay, so it's complementary to the Schrdinger algorithm, which has the opposite strengths. So basically, what this shows already is that if you combine the Schrdinger with the BGM algorithms, you get a classical advantage everywhere for sufficiently large circuits. Okay, and the actual size at which the classical advantage occurs is set by the parameters lambda and gamma, which is dependent upon the particular properties of the chip. So let's keep that in mind. There is, however, a serious caveat here, and that is that I haven't talked about memory issues. I've only talked about runtime. And it turns out that the Schrdinger algorithm requires us to store all 2 to the n amplitudes, and that becomes infeasible already for n greater than 50 or so. So that's the weakness of the Schrdinger algorithm. The memory requirements explode. Conversely, the BGM algorithm, what's hidden in this notation is that there's actually a huge prefactor over here, which means that the BGM runtime is, in practice, very, very large. So that makes it not so feasible, despite these asymptotic results here. So we need some kind of a intermediate algorithm, and that's where tensor networks come in. And the simplest version of a tensor network algorithm is what's called the Schrödinger-Feynman algorithm, SFA. And so essentially the idea is to divide the circuit into patches. Each one of these patches is simulated to full fidelity using the Schrödinger algorithm, and then you need to combine the different patches. And so I'm not going to get into the details. There's a very complicated looking formula here, which I'm happy to talk about later if anybody's interested. But we understand the scaling of the classical runtime scaling of the Schrödinger algorithm, Schrödinger-Feynman algorithm, very well. Most importantly, it depends on this exponentially on this factor here, m times root n, and that is a general feature of tensor network scaling. They scale like some factor times m exponential m times root n. And of course, it shouldn't get worse than a scaling that goes like 2 to the n. So here the circuit depth is upper bounded by root n, right? For this to make sense. If the circuit depth gets larger, then there will be a different formula which is more favorable. Okay, so we have Schrödinger, we have Schrödinger-Feynman, we have BGM, we have general tensor networks. One more thing. Now we need to define some appropriate way of comparing the quantum and classical algorithms. They all take exponential time. Okay, so if you're going to compare 2 algorithms which both take exponential time, then what you should expect is that one might be polynomially better than the other, right? And that's what this scaling exponent alpha c is attempting to capture. So let's postulate that the classical algorithm for XEB scales like the quantum algorithm time to the power 1 plus alpha. And alpha then is just this. And the way we defined it here, there is a quantum advantage if alpha is positive, right? Because then the classical runtime is larger than the quantum. And there's a classical advantage if alpha is negative. Okay, so this quantity, this alpha, will be useful in a moment. And then finally, we need to take into account the actual clock speed of the different processors that we use. So let's just take the quantum time t, or the classical time t, and multiply it by tau, which is the clock speed. And here you see there's a huge difference, a factor of 10 to the 10 between Sycamore, the quantum chip, and Summit. Sycamore has a clock speed of 10 to the 5 hertz. I'm sorry, these should be these are units of frequency, so of course it should be 1 over that. And Summit has a frequency of 10 to the 15 hertz, roughly, depending on the algorithm. So that's going to make a significant difference, although it is just a prefactor, right? It doesn't affect the scaling. Okay, so now we can put all these ideas together and plot the map of the boundaries. So let me walk you through what you're seeing here. First of all, what is being plotted is in the plane of m, which is roughly the depth, right? The depth is 2 times m. And n is the number of qubits. Now, what I'm comparing here is the Schrodinger algorithm versus the quantum runtime. And the green dots are the quantum runtime on Google's Sycamore circuits. So every dot here is one set of experiments at a given size, m and n, going all the way up to the largest, which is this dot right here, which was the size m equals 20 and n equals 53. But they ran a whole bunch of experiments. Now, the red line is the alpha equals 0 boundary, which, remember, alpha, when alpha is positive, we have a polynomial quantum advantage. When alpha is negative, we have a polynomial classical advantage. So the break-even line is this red line here. And it shouldn't surprise you that things are good quantumly for a large n, because the Schrodinger algorithm has an exponential scaling in n. But things are good classically for large m, because the Schrodinger algorithm has a linear scaling in m, whereas the quantum algorithm has an exponential scaling in m. Okay, so the red line tells us that Schrodinger algorithm will win to the right of it and will lose to the left of it. There's some additional lines here which I'll get into. Right now I just want to highlight the black dashed line, and that's what happens if we include the actual clock speed. Remember that factor of 10 to the 10 difference in clock speeds. So the very high clock speed of Summit helps it, and it makes the quantum advantage smaller. The zone of quantum advantage is smaller, so for sufficiently small circuits, it's still possible to beat the quantum circuit using classical simulation. Right, so essentially the quantum advantage is just above and to the left of the dashed black line when we compare to the Schrodinger algorithm. Now we can also do the same exercise with the Schrodinger-Feynman algorithm. Remember, that one scales like basically 2 to the m root n. So it behaves better classically as a function of n than it does as a function of m. And indeed, the boundary now is the red line here, which is one for sufficiently large n. Okay, so for sufficiently large n, because of the square root n scaling, Schrodinger-Feynman has an advantage over quantum. And likewise, we can take into account the clock speed, which gives us the black dashed line. And then when we put everything together, that is Schrodinger and Schrodinger-Feynman, we find that the quantum advantage is limited to these hatched lines here, this region of the diagonal lines. Okay, and quite surreptitiously is the wrong word, but fortunately, and actually that's also the wrong word, by design, the Google experiment you see has green dots within the this diagonal line area where indeed there is a quantum advantage. Right? So now you see that this quantum advantage region is actually small, but the parameters of the experiment were well chosen to lie within it, at least relative to Schrodinger and the Schrodinger-Feynman algorithms. Okay, so this, however, is not the full story, because as I mentioned before, we also have to account for memory constraints. And so we need to do that. And that if we account for classical memory constraints, it will turn out that it significantly modifies the picture that I just showed you. This is without the memory constraints. This was just accounting for time, but not for memory. We also haven't really talked about the actual time it takes to run these quantum experiments, because that time scales exponentially. And so that will also impose some additional constraints now on the quantum advantage. And then finally, it's very interesting to see what happens if you play with the error rates, right? If you increase or decrease the gate and the qubit error rates, that will also modify the region of quantum advantage. So here is, if you recall from the beginning of the talk, here is the plot that puts everything together, but comparing quantum just to Schrodinger and Schrodinger-Feynman. So now the axes are the same as before. This is number of cycles versus number of qubits. And accounting for the memory constraints as well on the classical computation, we get these colored zones here. The orangish one is where the Schrodinger-Feynman algorithm has an advantage over quantum. The green one is where the Schrodinger algorithm has an advantage. The red dots are the Sycamore data. And there's also one, the X here, the blue plus, is one more classical simulation data point, which is tensor networks. The most sophisticated tensor network calculation that has been performed, and you see that it improves a little bit over Schrodinger-Feynman. Right, so it slightly narrows the region of a quantum advantage. And then these black lines here, these are contours of how much time it would actually take to run the quantum experiment. Right, so 1 second, 1 day, 100 years. So the Google experiments, this is all with the actual parameters of the Google Sycamore experiment. You see that accounting for classical memory constraints, of course, makes things worse for the classical simulation. So unsurprisingly, the Google Sycamore data is still within the white zone, which is the white region, which is the region of a quantum advantage. What has changed compared to the previous plots here is you see here there was an upper bound on n and on m for the quantum advantage. The upper bound in terms of n has disappeared, and that is because of memory constraints. So the situation has actually improved for the quantum advantage. Okay, now we can ask ourselves what happens if we take the most entangled circuits, the most entangling circuits. The most entangling circuits are the ones where n scales like m squared, or rather m scales like root n. Those are circuits for which you entangle every pair of qubits within the circuit. And so what's plotted here is just as a function of n, which is now equal to m squared. Sorry, yes, and on the x-axis is the error rate relative to the sycamore error. And you see that as you decrease the error relative to what actually was available on sycamore, you can get a quantum runtime such that you solve the Xeb task of 1 second, which goes to larger and larger circuits as you decrease the error rate, right? So unsurprisingly, as you decrease the error rate, you can observe the advantage for larger and larger circuits. It would take 1 second at 0.1 error rate of sycamore, you would roughly get to about 400 qubit circuits. With 1 day, you could get to about 800, and that's kind of interesting, because typically when people talk about where quantum error correction is going to kick in and enable us to do more general tasks than quantum supremacy, like maybe run quantum simulation and so on, you need about 1,000 physical qubits per logical qubit or so. So you could argue that roughly around this point here, when the error rates drop to 10% of the sycamore error rate, is where you anyway expect quantum error correction to kick in, and because you will have about 1,000 qubits available and so on. So it's, in other words, what I'm saying is that roughly around this point, we might see a transition from quantum supremacy experiments to quantum error correction experiments doing useful things. Now, what happens if you? Oh, sorry. What happens if you if we were not so lucky, or if the Google engineers weren't so good? Let's say that the error rate was actually 3 times higher, okay, or 2.8 times higher. In that case, none of this would have worked. So if with the same chip, with error rates that were only 3 times higher, you see that the experimental data would lie within the region of classical supremacy. So the choice of at the point in time at which to perform these experiments was very good, because it wouldn't have worked with error rates from just a couple of years ago. And if we're talking about extrapolating in time, then here in this inset, what is shown are the extrapolated 2-qubit error rates from a whole bunch of different papers that reported such error rates up until the present, and extrapolated to 2024. And in 2024, if things continue on track, the error rates will have dropped to 0.28 of the current sycamore error rate. And there you see that we're well in the zone of quantum supremacy, right? And indeed, with those error rates, it would take about 1 day to get to about 800 qubits, which is, as I was remarking here, is where you would expect quantum error correction to kick in seriously and enable quantum simulation and so on. So in other words, this projects that we will be doing quantum supremacy experiments for a few more years, maybe until 2024. And by then, the error rates will have been sufficient to transition perhaps smoothly to a quantum error correction era. And we will not have to demonstrate quantum advantage using quantum supremacy anymore. Okay, so to sum up the implications here, quantum supremacy is always a region in this n and m plane. It is bounded below by classical advantage. It's not bounded above anymore because of classical memory constraints. Decreasing the error rates is something that is very useful. As you see, it greatly expands the white zone where we have a quantum advantage. In fact, the area of this quantum advantage regime grows exponentially as a function of these error rates. And an interesting observation here is that you see things are much better as you go vertically rather than horizontally, meaning quantum algorithms that are shallow depth, which don't require a large value of m, are the ones that are going to probably fare best before we get to quantum error correction. And certainly that is true specifically in the context of the quantum supremacy experiments, but possibly also beyond. And finally, this work suggests that there are some opportunities here. I'd like to leave you with some thoughts for what people might want to work on. The error model that I discussed, this Markovian stochastic error model, is very naive. And clearly it doesn't really capture what's going on. I think there's a really nice opportunity here to develop more realistic error models that account for non-Markovian errors, 1/f noise, and so on. Those are dominant in these transmon qubit experiments. Those are needed to get more accurate estimates and bounds. Okay, so that's all. I would like to thank my collaborators, Alexander and Sergio, and hopefully there's enough time left for some questions.
Okay. So for any questions, you can either raise your hand or you can just unmute and ask. So maybe I'll start. So you said before that there will still be some experiments to be done, right, up till like say 2024.
Mm-hmm.
So what would be some examples of these next experiments?
Well, I mean, obviously, it would be nice to just improve the demonstration of supremacy itself. And so you saw that the supremacy results were just inside the advantage zone, right? And so we would like to clear that bar much higher. That would be the obvious thing to do. And that can be done by decreasing error rates. But at the same time, we would then have to also, in order to make it interesting, increase the circuit parameters, so the circuit depth and the circuit width. So I think that's a very natural next step. Larger circuits, and concomitantly the error rates would have to drop. So that's one type of experiment, and it would be interesting to demonstrate it on platforms other than Google's. So perhaps on the other cloud computers. The other thing which I think is very interesting is to start to inject some kind of error suppression methods, software error suppression methods. So for example, you might want to see what happens if you use dynamical decoupling techniques, which are well known to work in an error suppression context. You don't have to use quantum error correcting codes. We're not quite ready for that yet. But you can use other tricks like optimal control and so on, and see if you can get better supremacy results that way. When I say better supremacy, what I mean is dive deeper into that white zone of quantum advantage. And then other experiments would be ones that kind of try to tease out the effects of specific errors. So what kind of error mechanisms do we need to worry about here, and which are more or less important? And then finally, as I mentioned on the last slide, there is the question of trying to run other algorithms. Not the quantum supremacy algorithms are interesting, but they don't they produce random numbers, and there are some ideas on how to use that for cryptography, but they don't solve a simulation problem or an optimization problem or something that is relevant in those contexts. So it would be interesting to try to take some of these ideas and branch out to other algorithms.
Mm-hmm. Okay. So what do you think would be like the next what would be the most likely next step in terms of, say, an algorithm that's useful, say, for, say, quantum chemistry? Like the most likely extension of this?
People are doing quantum chemistry experiments already using, that is, quantum simulation of quantum chemistry.
Mm-hmm.
So what this story is about is really kind of a critical evaluation of what it means to demonstrate a quantum advantage. And that applies broadly, including to quantum chemistry.
Mm-hmm.
When you read about a claim that somebody has done a quantum simulation of quantum chemistry and claims to have done something that is classically hard, then you want to evaluate that with a skeptical eye and perhaps use similar techniques to what I discussed here, which is to understand the scaling of the relevant set of classical algorithms, right, and map out the boundaries of where such a quantum chemistry experiment really does give a quantum advantage. And because quantum chemistry experiments tend to be not shallow depth, they tend to be deep,
Mm-hmm.
it seems that at this point it's going to be hard to demonstrate a genuine quantum advantage, right? And so here the message is basically try to map out these boundaries and make a convincing argument that you're really within the safe zone, whether it's quantum chemistry or something else.
Mm-hmm. Okay. Any other questions?
Yeah, I have a question. Yes, so first, thanks for the very nice talk. I got the point that when you say the quantum device successfully finished that Xeb task, that means that it provides a bit string in a sense that it's statistically non-trivial. Like you have that it needs to exceed the deviation, its deviation. But what about the classical side? How do you define that a classical device has successfully passed that Xeb test or like finish that task?
Right. So first of all, there are algorithms for which, classical algorithms for which that question doesn't arise because they simply do a full fidelity simulation. So for example, the Schrdinger algorithm, it just simulates the circuit with fidelity 1, and there's no question there about having to pass this kind of statistical test. For classical algorithms that don't do a full fidelity simulation, it's exactly the same criterion, right? So you need to sample enough times that your standard deviation is smaller than the fidelity that you're trying to estimate, and that's already accounted for in the results that I presented.
Yeah, I see. Thank you.
Any other questions? So maybe I'll wait 5 seconds in case anybody wants to unmute. Okay, so let's thank Professor Lidar again.
All right, thank you.